Yeah, thank you very much. Gesundheit, thank you. Gesundheit is it's the German in me. I always thought it was so sensible to wish Gesundheit instead of God bless you, because you know what Gesundheit means in German?
What?
It means good health, sound health. Like I'm wishing you good health. You see somebody sneeze, which I always thought was so logical, so German to do that. You sneeze, I wish you good health. Versus the God bless you thing. It's kind of weird, like you're expending a demon.
Well, that's why they do why.
I will accept either, of course. Thank you for your...
They did that because it was thought to believe that your heart skipped a beat. So they would always say, God bless you, in case your heart didn't restart.
Well, I heard it was like a sign that you are getting sick, like the black plague. And so like, oh, you're going to die. God bless you. Hopefully you don't die. I don't know.
Yeah. The Ring Around the Rosie song, you've heard that, right?
Oh,
The Ring Around the Rosie, that morbid nature of that song.
Most of those little tales have morbid natures.
I'm depressed. And I have to sneeze again. I think we'll be okay. Okay, so Chester, 14 to 24, with TV, without TV, my friend?
A little over 0 to 9.
A little over 0 to 9. Perfect. We'll just call it 0 to 9. Okay, so this is cardiovascular disease without TV. And the with or without TV is the experimental factor of whether they watch the minimum of 2 hours per day or something along those lines. Chester's question is a fantastic one. It's a fantastic one in that it asks, what does that picture tell me? What does that picture tell me? The article's headline claims prolonged television viewing linked to increased risk of type 2 diabetes, cardiovascular disease, and premature death. So that's what the actual article headline claims right there. Let me see if you can see it. Boom. Okay. These intervals right here actually support that. And here's why. According to these intervals, what is the lowest, actually I did this on the wrong side, didn't I? What is the lowest percentage incidence of cardiovascular disease with the minimum of 2 hours per day of watching television?
14.
At minimum, it's 14%. Minimally, it's 14%. What's the maximal level of cardiovascular disease if you take TV out of the equation? 9%, which means there's minimally a 5% difference in risk of cardiovascular disease with versus without television. That's what the point of them not touching is, Jessica. If they don't touch, you know that the rate here has to be higher than the rate here because they're not touching. If they, go ahead, what's on your mind? What's on your mind?
Does that really link them though?
It links them, it doesn't prove one causes the other. No, I see what you're hung up on, Jesse. You're hung up on the claim. I love this, by the way, thank you for that. She's hung up on the causality versus correlation. All this article claims is there's a correlation between watching too much television and increased cardiovascular disease, premature death, and risk of type 2 diabetes. That's all it says. Did you notice, though, I'm going to swing this back to the front. Did you notice one of the claims made by the author, which I find hilarious since he was the lead author on the story? Down here, the message is simple. Cutting back TV watching can significantly reduce the risk of type 2 diabetes, coronary disease, and premature mortality. False! False! As Chester just pointed out, there's a difference between saying they're linked and saying what?
That's the reason.
That's the reason that something is happening. There's a difference between saying that there's a link and the reason that it's increased cardiovascular disease is because of the TV. What other factors could there be? Stuffing your face while you're watching TV. Not doing anything while you're watching TV. I mean, the whole point of I believe, was to kind of combat that. The whole point of that gaming system was to get kids off their butts. If they're watching TV and playing video games, at least they're moving around while they're doing it. Many, many other factors. All the article says is there's a link. Not a cause, but a link. Is that fair, Chester?
Yeah.
Great question. But when they don't touch, you know that there is a significantly higher percentage here than here. Even at the lowest, this is still higher than that at the highest. Do you see how that goes out the window if they overlap each other?
Yeah.
As is happened on your last quiz, the variation quiz. I asked, is the headline Pelosi the least liked member of Congress accurate? It wasn't, because John Boehner, if you look at the intervals, his interval actually encroached on hers, which means he could be a slight higher percentage more disliked than Pelosi, depending on where they fell. And we'll study this a lot more in Math 244. but you are 95% confident that this rate is somewhere between these lows and highs. You're not exactly sure where, but it's somewhere in there. But even at the lowest, it's higher than this at the highest. Jess, is that fair? Fantastic question, my friend. Thank you for that. Thank you for that. Anything else in here give you guys grief? Man, there's not much to it. I mean, there wasn't anything in the text, I don't think, at all. I think it was all Sean creations. Because your book didn't have a section on this. And I thought to myself, holy crap, how can you not have a section on outliers? It's absolutely amazing to me to not have a section on outliers when it's pretty much the basis of research. I mean, the whole point of research and testing for things, whether it's a rehabilitation method, whether it's a medication, whether it's an exercise regimen, is looking for outliers. So I just thought it was kind of funny to not talk about. So we went ahead and talked about it with you guys. And I'll put a quiz up on this for next week for you. Cool? Yeah? Anything else give you grief? You guys can make histograms okay? We're going to make more of them today anyway. More histograms and making the box of whiskers. Get the box of whiskers okay? Yeah, it's all just stack plots. Good stuff. All right. Let me fire this up. Mute this. Because what I want to do is I want to take us to the next step, which is we just spent 5 glorious weeks immersed in statistics. We did. I mean, I don't know if you call them glorious, I would. I had a glorious good time. Hopefully you guys learned something too. So, we just spent 5 glorious weeks dealing with statistics. What I want to do today is I want today to be the first of the remainder of our time together, linking statistics to probability. And as excited as I am about statistics, and I put a little check mark next to it because we've spent a lot of time dealing with statistics. We haven't done a lot of time dealing with probability yet. Outside of your projects, we hardly mentioned them in class. I did that intentionally. I didn't want to do that until we had more time to kind of build up the language of probability. I want to link these two things together. I renamed this course last year. It used to be called Mathematics for the Management, Life, and Social Sciences. And I said, wrong. This is an introduction to probability and statistics, and I wanted that in the title because I want you guys to understand that's what you're studying in here. You're studying the idea of how to describe the world and how to predict what's happening in the world. That's the link. That's the link of these two things, is being able to see the description and also the supposition and inference. This is where kind of the beginning of the melding happens. So, I want to, actually, while I'm writing this down, could you guys pass this around? Take 2 dice out of this bin. Make sure they're 2 different colors. That's going to make things easier later for our discussion. And as you're walking that tin around, I want you to consider the following question. If you take a 6-sided die, okay, so we're making an experiment here. Experiment. And you won't need the dice to answer this question. You won't. Although we're going to simulate the experiment with the dice. But here's an experiment. Roll a 6-sided fair die 1 time. That's an experiment. Roll the die. What I want to do is I want to answer this next question a number of ways today. What is, and make sure this is okay language-wise. I also want to revisit the first project and cast an introduction to the second project with this. What is the probability that you get a 3? What is the chance? Good. So when you see that P with parentheses around it, I know it probably gives you heart palpitations and murmurs about Math 111 and function notation and all that stuff. It's not that at all. It's just a shorthand for the probability. You remember that in your first project. What's the chance? I like that too. Think about the chances, Athena. What? You can think about it that way. What are...
So is it 1 in 6 then?
Good, I like that answer. What are the chances of... Blah, blah, blah. And then that's going to be the same for any event we talk about. So we have a vote. Athena's got a vote for 1 in 6. Do we have a second? We have a second. Mike has a second. All in favor of the answer of 1 in 6 for rolling a single die? Any opposed? Still need for discussion? Yes, lots of discussion needed. But I appreciate you Angie, saying, no, we got this, I'm on the 1 6. Okay, it's good. I want to break this down. I agree with that. I agree that it's 1 and 6. How else could you state that result? 1 and 6 is fine, 1/6. How else could you state that result if you didn't like fractions?
17%?
Say that again, Lucas.
17%.
Love it. It's about 17%. Depends, maybe you want to go 16.7%. I mean, there's a whole bunch of this. It's 0.1666666 repeating. So take as much precision as you want from it and realize that if you round it off, it's never going to be completely accurate. Another way of looking at it is as a decimal, 0.17 or 0.167 or 0.1667, however many decimals you want. I love it all. I love it all. I love it all for different reasons. 1/6 is nice because it's completely self-contained. The other ones are a little more realistic, honestly. And you'll see more of that as we kind of come into our discussion of probability with greater detail. It's the same idea we talked about in your first project. You know, what's the chance that Punxsutawney Phil gave a correct prediction, assuming that he predicted an early spring? And it was something, I don't know what it was, 75% or something like that, 0.7534. It wasn't exactly that, but it was close to that. So I want to come back to this one, because this is a very, very nice, simple example. What does that mean, 1/6? What's the 1? What's the 6?
For every 6 times you roll it, there's a possibility of rolling, there should be a possibility of rolling it 3.
I love this. Did you guys hear that? So, if I roll it 6 times, what should happen, Athena?
Well, that's the problem with probability.
That's the problem with probability. Perfectly stated, my friend. I want everybody to do this, if you would. I want everybody to simulate what Athena just said. Take your die, roll it 6 times in sequence, and keep track of what you got. Okay? And keep track of what you got. This is fantastic. I'm going to cheat a little bit up here.
It's truly random.
Good. Oh, I love that too.
Unless you get it knowing.
Okay, I'm going to cheat up here using something you guys played with last time. Make sure you write down what you got too, right? Oh, ran in. There it is. 6. We're doing it 6 times, right?
That works really well.
There.
I like
Speaking
that.
of, oh, dude, this is fantastic.
Works great.
Yeah. Now, there's a difference, as Lucas just pointed out. This is a fantastic way of simulating random events. In certain cases, which I want to come back to momentarily, there's definitely something we're taking for granted here that you guys don't realize you're taking for granted right now, and that's okay. That's what today's all about. Is representing or recognizing that simplicity that that simplistic nature that we're assuming. You can't see that though. Let me move the TI down. Yeah, this is good. I like this. Okay, fantastic. So, what I want to know is, how many of you on your 6 rolls got 3? And I don't care about how many 3s, just how many of you got 3s? How many of you didn't get 3s? Okay, very, very nice, very, very nice. Hands again. Those of you that got 3s? Those of you that didn't get 3s? What do you guys notice? About average. It evened out. We're going to do that count in a second, too. I just did it as well. I did not get any 3s up here. I like it too. How many of you got 1 of each number? How many of you? What did you get? Give me the order you got, Sarah.
5, 3, 4, 1, 6, 2.
Boom.
Awesome.
Boom. How likely is that? How likely is it to get 1 of each number? Because that's what Athena was getting at. I love what you just said. What she just said was, okay, on 6 rolls. Actually, say it again. I'm going to screw it up. I'm trying to say what you said.
You have a possibility of getting a 3.
You do. What is the chance?
1 and 6 is the possibility, but what's reality is it's not going to be that.
Okay, I love this.
But if you were to roll it like 100 times and then check it, you'd probably get closer to that 1 and 6.
Yeah.
When you say check it, what do you mean check it?
Check your percentages.
Thanks for having right now. I want to analyze this.
Okay.
And Athena's done a really, really, really good job for us already. Here's the deal. I always like to think of statistics and probability as if you can explain it to your next door neighbor who's never taken a ProbStat course, then you've succeeded. And that's the hardest part, because we can chit-chat using very formal language in here. Very formal language in here. but unless you can explain it to someone else,
So the possibility, there is one possibility. The possibility one's been 6, because if you rolled it each time and got one number, like she did, each time different.
yes.
There's a chance of at least getting 1 and 6, but the thing is you could roll all ones.
Okay, hold that thought.
So,
I want to. You're about 7.5 minutes ahead of where.
Sorry.
No. I think it's great. It's fantastic. There's a reason I wanted you to roll it 6 times, because we were trying to see if. So I think we just disproved something. Does 1 and 6 mean if you roll a die 6 times, you will get 1 3?
No.
It does not mean that, does it? It does not mean that. So what does it mean?
possibility.
It's good. So what we're talking about is possibility, Lucas.
Yes. Over
Oh, I
time.
thought you guys want to fight. Yes.
Yeah.
We're getting back to best overtime on average. Oh, I love it, love it. So here's the deal. What does the stick stand for, friends?
How many different
Good. This is how many. And I'm going to use a phrase here that you probably take for granted, but it shouldn't be taken for granted. And you'll see more of this as to why on Wednesday. It won't apply to this particular example. How many equally likely outcomes are present in the experiment? So when you roll a 6-sided die, there are 6 outcomes, all of which are equally likely. Every one is just as likely to occur as the other one. That's often called the sample space. You might remember this term from your first project. Sample space. Sometimes also just called N, which is our sample size. I like that intersection of statistics and probability. Very, very nice. So the number in the top of the fraction, therefore, has to be what? What's the number at the top of the fraction? Well, it's 1. But what does the 1 stand for? In this case, how many equal outcomes? How would you describe the number that goes up in the top?
The event space.
Good, good. I love that. I love that. And I apologize for that phrase. I invented that phrase. I called it the event space on your last project because it needed a name like sample space. What's an event? Remember
What
Taking place,
happens?
yeah.
what happens that you're interested in, right? It's what you're studying that you're interested in. So this is number of ways of interest. Okay? Or number of events. And that's that phrase from your first project. It basically, this is whatever you're studying. So if you're talking about rolling 3s, it's the number of ways to get a 3. Talking about rolling a 5, it's the number of ways to get a 5. Talking about rolling a 6, number of ways to get a 6. Doesn't really matter as long as you define your event to be thus. To be thus. Awesome. Awesome. So we've got this 1 and 6. We now know what the 1 and 6 mean. It really is important that we notice that it's an equally likely kind of thing. It is an equally likely kind of thing. So I want to come back to this again. What does the 1/6 mean again? And you guys in 105 had a nice jump start on this. This is fantastic. So tell me, Lucas, tell me again.
That over time, you will get a 3 or get any desired number 1 out of 6 times. It's like, and you have to take like.
Tag that on too, Chris.
On average.
Good. On average. Good. Here's the deal. When you guys all rolled your dice 6 times, and I said, how many of you got at least a 3? How many of you got 2 3s when you rolled the dice? Anybody get 3 3s when they rolled the dice? Anybody get more than 3? So we got a bunch of 0s, we got a bunch of 1s, a bunch of 2s, no 3s or 4s or 5s or 6s. That becomes what's called a binomial experiment, and we'll get back to it. I promise we'll get back to that soon enough when we talk about the binomial distribution, although I don't want to get too far ahead of ourselves right now. What I want to do is, I want to test this statement that these guys just put forth. The 1/6 is not so much a promise, and again, you mentioned this, it's not a promise, it's an average. And that's what I really want to do is, I want to be able to link the idea of an average from statistics into this beauty of probability right now. So let's collect a little more data with your permission. What I'd like you to do right now is take those dice. You already have 6 outcomes, right? If you guys would, roll them 10 more times and keep track of what you got.
Both of them this time?
No, just roll 1. Just roll 1 again. We'll do 2 dice soon enough. We're gonna have to break. But roll that single die 10 more times and write down the results you get. And let's see if we can see. Let's see if we can see those results that Lucas was talking about kind of arise.